Okay, let's now talk about some other properties of the discrete time Fourier transform. The first thing I want to talk about is DTFT of pure sinusoids. So we already said that DTFT gives us information about the types of frequencies, the amount, the phase of different frequencies that are present in a signal. And we have talked about how pure sinusoids appear in continuous time Fourier transform. So a similar relationship applies. The first part is that any pure sinusoid, which is cosine, sine, or e to the j omega n, therefore DTFT appears as impulses in the frequency domain. And since we are in the discrete world, what it means is little omega domain. And the other thing is that when I was giving you the definition of the DTFT, I have said that generally DTFT is always defined for signals which are finite energy. Now a cosine, for example, it's not a finite energy signal. You can't add up all the values of cosine, square it, and still get something less than infinity. So we cannot explicitly calculate the DTFT of pure sinusoids. But what we do is we sort of make a guess and we verify that it is indeed the Fourier transform pair, because once we take the inverse Fourier transform of that, we get back the original signal. So let me give you an example of a pure sinusoid. So let's say xn equal to j to the omega naught n. So omega naught is any value between, let's say, minus infinity to infinity. But since we always talked about the discrete time frequencies, the most important part is between minus pi and pi. So we'll first of all reduce that omega naught to a value between minus pi and pi. Okay. So we are in the fundamental period or fundamental frequency between minus pi and pi. Now this is a complex exponential with frequency omega naught. So if we think of it, the DTFT of that should have an impulse at omega naught, because that's what the DTFT is going to tell us. So let's say omega naught was positive. So this is my 0. This is pi minus pi. If omega naught was positive, if this is omega naught, then I'll have an impulse here. And of course, this same impulse, because of the periodicity of discrete time frequencies, the same impulse will be repeated every 2 pi period. So I will have an impulse here, and I will have an impulse here, and so forth. So this is sort of what you expect intuitively, and what we say is that a pure complex exponential has a Fourier transform which is given by, so it's 2 pi delta of omega minus omega naught. That takes care of this impulse. But then you also have an impulse at every 2 pi k distance. So we also have plus 2 pi k and summation k from minus infinity to infinity. So the difference between the continuous time Fourier transform, of course, is that if I had given you e to the j omega naught t, the Fourier transform of that continuous time Fourier transform of that is just one impulse at omega naught. But in this world of discrete frequencies, we have impulses, we have an infinite number of impulses at omega naught plus 2 pi, omega naught plus 4 pi, and so forth. Okay? So how do we verify that this is indeed the case, that this is really the Fourier transform of a complex exponential? We use the inverse Fourier transform formula. So we call that x of e to the j omega, and the way to verify that is we want to make sure that when we compute the inverse Fourier transform, when we do 1 over 2 pi minus pi to pi x of e to the j omega n d omega, we get back e to the j omega naught n. So if that happens, then we say, yes, it is a Fourier transform pair. We'll be happy with the fact that what we proposed as a Fourier transform is correct. Okay. So to verify that, I just plug in this expression. I have minus pi to pi, summation k from minus infinity to infinity, 2 pi delta of omega minus omega naught plus 2 pi k, e to the j omega n d omega. Now, since integration is linear, I can, and without going into too many rigorous details, we'll just switch the order of summation. We'll say summation k from minus infinity to infinity and do the integration minus pi to pi delta of omega minus omega naught plus 2 pi k e to the j omega n d omega. Now this is a function for every k. This delta omega is either between minus pi and pi, or it is between pi and 3 pi and so forth. But my limits of integration are only from minus pi to pi. So this whole summation is equal to 0 except for k equal to 0. And there is, of course, this 2 pi factor that I just took out, so we cancel that. Now this whole summation, except for k equal to 0, will be 0 because your function is 0 your limits of integration only go from minus pi to pi, right? So I only care about the function value between minus pi and pi. I care only about this, and between minus pi and pi, I only have one impulse. All the other summations are outside that integration range. So what I get at is minus pi to pi delta of omega minus omega naught e to the j omega n d omega. Now we'll use the property which we generally studied of impulse, which is that if you are given an impulse delta of x minus x naught f of x, so you should just remember that if you multiply a function with an impulse, you have the shifting property of the impulse, which says, so that will be equal to delta of x minus x naught f of x naught. So if I use that property, I can further reduce that integration to delta of omega minus omega naught e to the j omega naught n d omega. Now e to the j omega naught n is not a function of the variable of integration, so I take that out. I get e to the j omega naught n minus pi to pi delta of omega minus omega naught d omega. And now we use the property that an impulse is defined in terms of the area under the impulse is 1. Right? So this whole integration is equal to 1. So I get e to the j omega naught, which is what we wanted to prove. So indeed, the Fourier transform of a complex exponential, a complex sinusoid is an impulse at omega naught and multiples of those omega naughts. Now, using this simple fact, you can actually prove the Fourier transform of, for example, cosines and sines using the Euler's identity. So the DTFT of, for example, if you're interested in cosine omega naught n, to compute that, we write that as e to the j omega naught n plus e to the minus j omega naught n over 2. And after that, you try to take the Fourier transform of two pieces. So for that, we need another property to evaluate that. But basically, just knowing the Fourier transform of the complex exponential is enough for you to compute the DTFT of cosine. Similarly, for sine, you remember that it's e to the j omega naught n minus e to the minus j omega naught n over 2j. So everything can be reduced to complex exponential, and then you can compute the Fourier transform. There are some other common discrete time Fourier transform pairs that you should be aware of. So table 3.3 in text lists some of those Fourier transform pairs. And a really important pair is the following that we'll be referring to later. So the signals for in time domain is sine of omega c n. So whenever there is a subscript with omega, that means that's a fixed number. Okay? So omega c is some number divided by pi n. Its Fourier transform is given by this box function. It's 1 for 0 less than or equal to absolute value of omega less than or equal to omega c. 0 omega c is less than absolute value of omega less than or equal to pi. And then it repeats itself because of the periodicity of the Fourier transform. So the Fourier transform of this function basically looks like the following. It's all ones from minus omega c to omega c up to pi. And then, of course, it repeats itself after every 2 pi intervals. So this is your h of Lp e to the j omega. Now this is again one of those Fourier transform pairs that are pretty difficult to derive if you use the Fourier transform formula directly. So the right way to go in this kind of expression again is actually use the DTFT and the inverse Fourier transform to verify that it is indeed the Fourier transform of your xn or hn, whatever you want to call it. Okay. So these are some just basic pointers about, sometimes you cannot use the Fourier transform formula directly, and you really have to start with the Fourier transform and compute its inverse Fourier transform to verify that they are pairs of each other. Now let's talk about some key properties of the DTFT, using which and using some basic pairs we can compute the DTFT of many other sequences. For example, the cosine and sine that I talked about. So the first property is linearity, which pretty much all transforms that you have studied have that property. What linearity says is that if you are given two sequences, So you have a sequence Gn whose Fourier transform is G e to the j omega, and you are given a sequence Hn whose Fourier transform is H e to the j omega. And if you are asked to find the Fourier transform of alpha Gn plus beta Hn, where alpha and beta are some scalars, real or complex valued, then all you have to do is take the Fourier transform of the individual sequences and multiply them with the right scalar. So what you do is the Fourier transform of this thing is equivalent to alpha times the Fourier transform of Gn. So alpha times Fourier transform of Gn plus beta times Fourier transform of Hn. And then you can simply compute the Fourier transform of that, which is alpha G e to the j omega plus beta H e to the j omega. So using this linearity property, now we can compute the Fourier transform of cosine. So given xn equal to cosine of omega naught n, where omega naught is some value between minus pi and pi, I can write that as sum of two sequences e to the j omega naught n over 2 plus e to the minus j omega naught n over 2. And now I use this linearity property, which means that that is equal to 1/2 Fourier transform of e to the j omega naught n plus 1/2 Fourier transform of e to the minus j omega naught n. And we just computed the Fourier transform of e to the j omega naught n. So we get that's 1/2 times 2 pi summation k from minus infinity to infinity delta of omega minus omega naught plus 2 pi k plus 1/2 times 2 pi summation k from minus infinity to infinity delta of omega plus omega naught plus 2 pi k. And now I can just combine all of them. So the Fourier transform of a cosine will be k from minus infinity to infinity delta of omega minus omega naught plus 2 pi k plus delta of omega plus omega naught plus 2 pi k. And if you compare that with the continuous time Fourier transform, if you remember that if I was given x of t equal to cosine of omega, capital Omega naught t, then the Fourier transform of that is equal to pi times delta of capital Omega minus omega naught plus delta of capital Omega plus capital Omega naught. And you see the similarity between the two Fourier transforms, that indeed since you have a pure cosine at omega naught, you get impulses at omega naught due to the positive complex exponential and at minus omega naught. But in the discrete time Fourier transform, you have this additional summation due to the fact that discrete time frequencies are periodic with period 2 pi. Right? So if I were to plot x of e to the j omega for this, between minus pi and pi, it's exactly like the continuous time world. I have an impulse with area pi at omega naught. I have an impulse with area pi at minus omega naught. But then all of this will get repeated because of the periodicity of the discrete time Fourier transform, of the periodicity of the discrete frequencies. Using the similar linearity property, you can derive the Fourier transform of the sine. I won't go into the details that you can do that. So let's look at another property. The other property is time reversal. So suppose you are given a sequence Gn, which has a Fourier transform G of e to the j omega, and you reverse that signal. So you flip it around its axis, G of minus n. For example, you had a song and you just flipped it backward, right, around the origin. And if you look at its Fourier transform, that is equivalent to flipping the Fourier transform around the frequency axis. Okay. So what this means is that flipping in n is equivalent to flipping in omega. And in particular, if you have a real valued, if you have a, let's say, an even function, right, you flip it, you are going to get back the same function. And if you look at the Fourier transform of that, you are going to get back the same Fourier transform. So those some of those little tricks you can play. But basically, it explains what happens when you flip a time domain signal, what are the changes that are happening in the frequency domain. Okay. The next property is time shifting. So if you have a Fourier transform G of n, again, up here, its Fourier transform is G of e to the j omega. And I shift now the sequence by some amount n naught. So suppose I have a sequence, I have a song, and I shift it by 10 seconds, let's say. Now, what happens is that causes a phase shift to your Fourier transform times your original Fourier transform. So let's try to understand what does this formula tell us. So let's first look at the magnitude of the Fourier transform of the new sequence. So first of all, ask yourself, if you have moved the song by 10 seconds, the song is still the same. The frequencies that are present in that song, would they somehow change? If I speak right now versus you listen to me, you delay, let's say you record my speech and you delay it by 10 seconds, are the frequencies that are present in my speech or in a song, are they going to change their amount just because I'm delaying that by 10 seconds? So intuitively what it means is that if you delay a sequence, the magnitude of the frequencies should stay the same. So let's verify that from this formula, that the magnitude of this new sequence Fourier transform is e to the minus j omega n naught g of e to the j omega, and we now divide it into two pieces. So absolute value of e to the minus j omega naught and absolute value of e to the j omega. And of course, absolute value of e to the minus j omega naught n, that is equal to 1. So I get simply absolute value of e to the j omega. So which is verifying that shifting a sequence does not change the magnitude of different frequencies. So what is shifting doing? So a complex number has magnitude and phase. So let's now look at the phase. So let's look at the phase of the new Fourier transform, e to the minus j omega naught n, g of e to the j omega. So I can write the phase. So if you multiply two complex numbers, the phases get added, right? So the phase of the phase of e to the minus j omega naught n, what is the phase of that? So the answer of the phase of this new complex number is phase of one complex number e to the minus j omega n naught plus phase of j e to the j omega. And the phase of e to the minus j omega n naught is minus omega n naught. So what it means is that if you are doing a time shift of a signal, it does not change the magnitude of your Fourier transform. The only thing it does is it adds a phase shift of minus omega n naught to your original phase. So for example, if the phase of g e to the j omega, assume that this was equal to 0. Just make an assumption. Then your phase of e to the minus j omega n naught times g e to the j omega, that will be equal to, simply if you plot it in the omega axis, it will be just this line with a slope of minus omega n naught, slope of minus n naught. So all that a time shift does is creates a linear phase shift to each of your frequencies. It creates a phase shift proportional to the amount of the frequency. So a frequency of omega equal to pi will have a phase shift of minus pi n naught. A frequency of omega equal to pi by 2 will have a phase shift of minus pi by 2 n naught. That's all it does. So what this means is that time shift, the term that we use, gives rise to a linear phase shift in frequency. And this concept will come up again and again, that linear phase shift is something that is not an undesirable aspect, because linear phase shift simply means shifting. Okay, we'll see that come up again and again. Now, together, time shifting and linearity help us determine the DTFTs from difference equations. So sometimes you are given equations or signals or sequences in terms of difference equations, which you have already seen in terms of the Z transform. So let's say you are given a sequence V of n, which is described in the following sense: d naught, which is a scalar Vn, plus d1 V of n minus 1, that is equal to P naught delta of n plus P1 delta of n minus 1. just like you guys did the Z transform, right? If you are given a difference equation, what do? You take the Z transform of both sides and then you manipulate. Using the same properties, we can take the Fourier transform of d naught Vn. So the left-hand side and the right-hand side, we take Fourier transform of both the sides, delta n plus P1, delta of n minus 1. Now, using linearity, we can write down the left-hand side will be equal to d naught. So let's call it v of e to the j omega plus d1. Now, we are doing a time shift of Vn. So Vn minus 1 will be given by e to the minus j omega v of e to the j omega. So just the time shifting property. And similarly, we do here P naught. Now, we had computed the discrete time Fourier transform of delta n in the last class. So that is delta n Fourier transform is 1. So we get 1 plus P1. Delta n minus 1 Fourier transform is simply 1 times the phase shift. And now we do the same trick that we do for the Z transform. We collect V of e to the j omega. And we are left with d naught plus d1 e to the minus j omega equal to p naught plus p1 e to the minus j omega. And now we take it to the other side. So we get v of e to the j omega equal to p naught plus p1 e to the minus j omega over d naught plus d1 e to the minus j omega. So just the linearity and the time shifting property helps us solve the DTFTs of difference equations. And the principle is pretty much the same as the Z transform based difference equations that you have solved in your linear systems class. Okay, the next property, which is again a property that you have already seen in the continuous time world, that's called the frequency shifting. Or also called the modulation property. So what is that property? That you are given a sequence Gn whose Fourier transform is g of e to the j omega. So let's say the sequence is what you are saying on the phone, right? And you have a certain Fourier transform. Now, if you multiply your sequence in time domain by e to the j omega naught n, Gn. So what is this? This is a sinusoid with frequency omega naught. So if you multiply your sequence with a pure sinusoid of frequency omega naught, the Fourier transform of that is simply that your Fourier transform gets shifted by an amount omega naught, which is exactly the same modulation property that you have seen in the continuous time Fourier transform world. You multiply your sequence with omega naught and that shifts where your Fourier transform sits. And this is an extremely important property used in, for example, communication systems. So here is an example of that. Let's say that you have a signal. I'm only going to focus on parts of the equation. So you have minus pi to pi. Here is 0. And this is what your Fourier transform looks like, g of e to the j omega. Some small amount around 0, which is sort of true when you are talking on the phone, that's what, your speech is centered around 0. But when you're trying to transmit over the cell phone, each cell phone carrier has available some spectrum, so they can't just transmit around 0. They are given, okay, or radio stations, you hear, FM 90.3 or whatever, right? Those are the spectrums that they are given. So you want to shift your signal from around 0 frequency to a different frequency. And that's when you bring in the modulation property. So if I multiply Gn with e to the j pi n, which means that my omega naught equals pi. Right? If I do that, then what is going to happen is that the new signal will now, the entire Fourier transform will be shifted by an amount of omega naught equal to pi. So instead of centered around 0, now what I will get is a Fourier transform which is centered around pi. And of course, because of the periodicity, it will be centered around minus pi and so forth. So modulation helps you shift the frequencies of your signal. The total frequencies, the shape of the frequency spectrum stays the same, but you can shift it from one place of the spectrum to another place of the spectrum. That is the principle that all communication systems, radio or satellite, or for example your cell phones use, because every one of them is given its separate region in the spectrum. Not all of them can transmit at the same time on around 0. So they generate the signal and then use this modulation property to shift their signal around. The next property is differentiation in frequency property, which again you have seen a counterpart of that in the continuous time world. Which is that if you are given a sequence Gn which has a Fourier transform G of e to the j omega, and now if you multiply your signal by n, then that is equivalent to taking a derivative of your Fourier transform in the frequency domain times a phase factor given by j. Yeah. And there are a couple of other properties that we are left with. And the next property we want to look at is what's called the modulation property, which is a general version of the modulation property that we looked at before, which meant that you actually take your sequence and multiply it with a sinusoid, and what that does is shifts your frequencies around. Now this is a more general version of that, which is that if you have two sequences whose Fourier, so Gn, Hn, and their Fourier transform are G and H, and previously we had looked at the case where H was specifically a sinusoid. So now it is that if you multiply the two sequences in time, so we already know that similar kinds of things for the continuous time Fourier transform, which is that if you multiply two continuous time signals, the effect of that in frequency is the Fourier transform of that in the continuous time domain is convolution of the Fourier transform. Now in the discrete world, it's a similar kind of a property, but not exactly the same property. So the discrete time Fourier transform is periodic, which means that if we were actually to use the convolution formula, no matter where you shift those two sequences, when you take their integration, you will get an infinite amount of energy or area under the curve. So we have to modify the notion of, and again, we won't go into the proof of that. The formula looks very similar to the convolution formula. So you have one function g e to the theta. You have another function h of e to the j omega minus theta d theta. So what is this? This is saying, just like the convolution formula, you fix one function. The other function, you are flipping it around the axis, and then you are computing, you shift it by omega, and then you multiply the two functions. And the integration means you are now computing the area under the curve. Now, I can't have the limits of integration from minus infinity to infinity because they are periodic functions, they go on forever. You multiply two periodic functions, the area under the curve will, unless they really cancel out, could be infinity. So that's the only difference between what type of convolution it is. The limits of integration actually, instead of going from minus infinity to infinity, they go from minus pi to pi. In general, they could go for any 2 pi region because the Fourier transform is periodic over a period of 2 pi. You could use any 2 pi. So this thing, because of the nature, it's called periodic convolution. Okay. The convolution that at the end of the day you will get, that will itself be periodic. You are taking periodic convolution of two periodic DTFTs. The final DTFT you will get will also be periodic. So that's the key difference. Otherwise, it's the same, that you multiply two time domain signals, continuous or discrete. In frequency domain, you are getting convolution. But for continuous world, you are getting the actual convolution that you learned in the last class. For the discrete world, you are getting periodic convolution because your Fourier transform is periodic. Again, if you are a little bit in doubt, let's consider, let's say I have two functions a omega, or let's call them a capital omega and b capital omega. And if I want to compute their convolution, that is given by minus infinity to infinity. For example, a of tau, b of omega minus tau, d tau, right? So you should compare the two expressions above and below. It is exactly convolution. E to the j, as we talked about, is there just to remind you that it's the discrete-time Fourier transform. But it's exactly the same formulation, that you're fixing one, flipping the other, and sliding it. The only difference is the limits of integration. Okay. The next property, which is again something that you have seen in many transform domain classes, is called the Parseval's theorem or Parseval's property. The intuitive way of understanding Parseval's theorem, at least for certain type of transform, I'll just say, don't worry about if you don't fully know what it means, but orthogonal transforms. What it says is, it's sort of like the law of conservation of energy. Right? You have a time domain signal, and it has certain energy. Now, what is a transform? Transform is looking at the same signal, but in a different way. So the energy in that signal is not going to change just because you're looking at it in a different way. So in the Fourier transform world, we look at the signal in the time domain and then we look at it in the frequency domain. Now in the continuous time world, the term we use is the energy in time domain is equal to the energy in the frequency domain. It's the same principle in the discrete time world also. Discrete time Fourier transform is just looking at the signal, the time domain signal in the frequency domain, but it's the same signal, so its energy cannot change. And that's what effectively Parseval's theorem is. Right? Energy in time equals energy in transform domain, or in this case, the frequency domain. So if you are given a signal Gn, which has a Fourier transform Ge to the j omega, how have we defined the energy for discrete time signals? We take the sequence, we take the absolute value squared, and we sum up all the values. That's the definition of energy. Right? If we normalize that, then we get power. And what is the definition of energy in the continuous world? Since Fourier transform is continuous, the definition of energy in the continuous world, now it is periodic, so we take the Fourier transform, take its absolute value, square it, and then integrate it. But now the limits of integration only go from minus pi to pi. And also because the unit of our frequency is radians per sample, there is a normalization factor of 1 over 2 pi. And what the Parseval's theorem says is that the two energies are equal. And there's a general form of Parseval's theorem, which I'll just give for reference, which is actually that if you are given two sequences, G and H, and then you multiply Gn with H conjugate of n, and you multiply 1 over, you do the same, then that is equal to the same operation in the frequency domain. Now how do you derive this special case from this general form? You put H conjugate of n is equal to G conjugate of n, right? And also remember that absolute value of a complex number is simply that complex number multiplied by its conjugate. So that's how you use the general form to derive the special form.